lovely February afternoon. Anyway, this is our page 8 of our Earth Science Reference Tables, which talks about the geologic history of the Earth. So let's get right into it. First of all, on this side right over in here on the extreme left-hand side, you have the entirety of Earth's history from 4.6 billion years ago, or as they have it, 4,600 million years ago, to the present at 0 years ago. Now, this huge slice of time is broken up into two main eons, the Precambrian eon and the Phanerozoic eon. The Precambrian is so large that they've actually broken it up into other eons called the Archean and the Proterozoic. Okay? Now, what's interesting about this chart is that what we have here is what I refer to as the early stuff. This is 89% of Earth's history. Up here with the Phanerozoic, which of course bleeds out into all of what you see here, is about 11% of Earth's history. And that's more of the modern stuff. All right, let's take a look at the early stuff for a couple of minutes. First of all, 4.6 billion years ago is the estimated time of when the Earth itself was formed. Between 4.6 billion years ago and about 4.2 billion years ago, the Earth was very little more than a quaking mass of volcanoes, and these volcanoes were outgassing many gases which made up the early Earth atmosphere. One gas that was missing was free oxygen. There wasn't oxygen because, well, first of all, there wasn't any bacteria or green plants to put oxygen into the atmosphere. So we had to wait quite a while until that would happen. About 4 billion years ago, which is about right here, the early Earth's oceans began to form. They're nothing like what they are today, of course. Today's oceans are just teeming with life. Oceans back 4 billion years ago, there was really, there was nothing living. Till about 3.5 to 3.3 billion years ago, where you had your oldest algae forming in the oceans. And of course, because these were green plants, this was the beginning of putting oxygen into the oceans and into the atmosphere. And of course, from about this time until about 2 billion years ago, the oceans and atmosphere were being seriously oxygenated by this green algae. About 1 billion years ago, we have our first multicellular creatures, such as jellyfish, and it was at about this point that life really started to get moving. Now, what's not shown on the reference table is that about 800 million years ago, the Earth itself was covered by thick layers of ice from a very significant time of glaciation. If it wasn't for plate tectonic convection cells breaking the continents apart, that ice might not have melted. And that would have caused what little life there was on this planet to go bye-bye. Now, after the ice melted, and we get to about 542 million years ago, there was this huge explosion of life forms on this planet. All of a sudden, the oceans were literally teeming with life, and so forth and so on. Most of the creatures up to this point, up to 542 million years ago, the end of the Precambrian eon, were soft-bodied creatures, which made finding fossils of them to be a very difficult task. But starting at around 542 million years ago, which is actually right here at the base of our timetable for this side, as it says, basically we've got just this great diversity of life forms with shelly parts. In other words, creatures with hard parts, and so forth and so on. Now we're starting to talk about more modern times, if you could consider 542 million years ago modern times. The first era of the modern eras is the Paleozoic, and it means early life. The second era is Mesozoic, which means middle life, and Cenozoic, the era that we live in, means recent life. Now, when an era begins or ends, typically something pretty significant has happened. When the Paleozoic era began, there was this so-called explosion of variety of life forms in the oceans, such as earliest fish, first coral reefs, and so forth and so on. Trilobites were also dominant during this time, and you had lots of creatures living in the ocean. Now, the Paleozoic era contains smaller slices of time called periods. We start with the Cambrian, then we got the Ordovician, Silurian, Devonian, Carboniferous, which is broken up into the Mississippian and Pennsylvanian, and then the Permian. This was a time of very early life. It was also a time when you had your first creatures beginning to live on land, such as during the Silurian, and earliest insects during the Silurian period. You also had your first amphibians, you had your first forests, and so forth and so on during this time. Now, the Paleozoic era was humming along very, very nicely until about 251 million years ago. And if we look at the life on Earth portion of this, something very bad happened. And scientists in the last 10 to 15 years have figured out what that is. They figured out that this incredibly large volcanic eruption in Siberia acidified the oceans and damaged Earth's atmosphere to the point that 95% of all creatures on this planet became extinct. That was almost the end of everything 251 million years ago. So the Paleozoic era ended with this mass extinction. Now to review, the Paleozoic era means early life. It is broken up into these very periods here. And for reference, we know how many millions of years ago each period was because it tells us this on the reference tables when a period would begin and a period would end. The next era is the Mesozoic, which means middle life. It is made up of three periods: the Triassic, the Jurassic, and the Cretaceous. The Triassic period was the time of the earliest dinosaurs. This is when reptiles became very large, became either herbivores, carnivores, but this was the time of the dinosaurs. And dinosaurs, to many people, are quite fascinating. It's also, ironically, the time of the earliest mammals, which, of course, would take over when the dinosaurs became extinct. Jurassic was the time of earliest birds. It was also a time when lots of dinosaurs existed on this planet. Cretaceous was the last period of the Mesozoic era, and the Cretaceous ended along with the Mesozoic when there was a ginormous extinction of creatures. About 75% of life on this planet became extinct, including the dinosaurs. And this is because of a gigantic asteroid about 6 to 10 miles across, striking near present-day Yucatan, causing an enormous amount of dust and ash to move into the atmosphere. This would, of course, block sunlight. That means that plants would die out. This means that the things that would eat the plants would die out. This would mean that the things would eat the things that would eat the plants, and so forth on up the food chain. Now, our next era in time, is, of course, going to be the Cenozoic era. And the Cenozoic era is our time. It means recent life. We know so much about the Cenozoic era that not only do we break it into the Paleogene, Neogene, and Quaternary, but we also break it into smaller geologic time gaps called epochs. And of course, these epochs are very well known about. A lot happened in the last 65 million years. And of course, a lot of it is illustrated along on our reference tables, like first grasses, abundant grazing mammals, large carnivorous mammals, and 1.8 million years ago, humans, of all things. So this is a very, very recent time to us. Now, moving a little bit to the right of the reference tables, you have this chart which indicates when there was rock deposited during that time period in New York State. If we follow it from the Cambrian period up, there is evidence of rock all the way through the Carboniferous period of the Paleozoic era. But there's no Permian age rock, which is a shame because Permian age fossils are really cool. It was the dawn of the dinosaurs, and some of those fossils are really quite amazing. Some Triassic age rock, but not much. a little bit of Jurassic Age rock, quite a bit of Cretaceous Age rock. But when we get into the Cenozoic, no Paleogene or no Neogene age rock, but there is rock from the Quaternary. So this tells us when there was rock deposited and when there wasn't. This doesn't mean that there wasn't rock deposited during this time. It's just that there's no evidence of it. Perhaps it was eroded away. Now, moving on to page 9. Page 9 has our time distribution of fossils all throughout the middle of the reference tables. It shows us a timeline. It shows us when creatures began, like the trilobites began here, and when they ended, which of course is right here. The trilobites lasted some 200 million, 300 million years. Okay? But what's cool about this is that there are letters along each timeline. And those letters represent index fossils. And of course, here are the index fossils. Trilobites A, B, and C, they're right here. Elliptocephala, Cryptolithus, and Phacops. So they basically tell you what fossils they're talking about. These are index fossils. These are very common fossils during their geologic time. As you can see, some species live for a very long time, like the brachiopods. Here are the brachiopods over in this corner right here, the Eospirifer and the Macrospirifer. They live for a very long time. However, like the placoderm fish, like fossil R, really didn't do very well. So both Triolepis didn't survive for a very, here it is right here, very, very long time. So this is our timeline. Of course, it talks about the first birds coming in during this era, this period rather, and still with us today. Mammals obviously still with us today. However, most creatures have become extinct, like the trilobites, the ammonoids, the graptolites, the placoderm fish, the dinosaurs. So this time distribution of fossils is going to be very helpful because it tells us when certain creatures on this planet lived. And we can correlate the letters with the index fossils that are listed below.
Tell them why index fossils are so important, though.
Index fossils are important because they basically help us identify a very specific period of time. Because index fossils are very common, found everywhere, but live geologically for a very short time. We'll get into that a little bit later on in this unit. Then, of course, there are the important geologic events in New York State. This tells us about mountain building, like the Grenville orogeny, which is all the way down here, orogeny meaning mountain building, which details the very earliest birth of the Adirondack Mountains in the Hudson Highlands. Then, of course, you've got other mountains like the Conics, the Acadians, the Alleghanians, and so forth, and it's all listed in this part of the reference tables. You can tell what period these occurred by just following the important geologic events of the Earth all the way over to the other side. For example, the Devonian orogeny occurred during the Ordovician period, and so forth and so on.
Does that mean that New York State was on the plate boundary at one point?
It's possible. They definitely think so. I mean, mountains are created with the collision of two tectonic plates. That's basically what causes our mountains. Now, also, if you notice about important events in geologic time, Pangea begins to break up many millions of years ago. It talks about the initial opening of the Atlantic Ocean. And of course, most recently, it talks about the advance and retreat of the last continental ice, which is something which is extremely recent to us. Finally, all the way over on the right, on page 9, it talks about where North America was at various times during the geologic past. Of course, we can tell by looking here that North America has moved north-northwest in the last 458 million years. You can tell that, North America was with the other continents 359 million years ago. And of course, 232 million years ago, they were all together with one continent called Pangea. Then they began to break apart about 180 million years ago. And as you can see, 59 million years ago, they do sort of represent what they look like more or less today. So overall, the geologic time scale here is a very helpful tool when it comes time for finding the age of early creatures, finding eras, periods, and epochs, and so forth and so on. Thank you. Have a lovely afternoon.